All right. Question number 1. The variable occupation would be an example of qualitative variable. True or false? Logan? The variable occupation would be an example of a qualitative variable. True or false? True. Okay. It's a label, right? Qualitative data is just a label, a name, a category. So that would be true. Okay, very good. All right. Carrie Barton. The time required to run a marathon would be an example of what type of variable? Discrete, continuous, qualitative, homogeneous. Okay, continuous. Excellent. We say that a continuous variable is one that typically does what? Okay, it can take on any value within a range, and kind of the clue might be things that we tend to measure are continuous versus for discrete data, those are things that we would normally what? Count. Okay? So you need to know the difference between continuous and discrete. But time required to run a marathon would be continuous. Okay, the salaries of auto workers would be an example of what type of data? This is Miss Belton. Okay, D, very good. Ratio level. Okay, yesterday we had to go through all 4 levels to get to the right answer. But just as a review, nominal level data is just a what? Category, label. Ordinal level data is something that we can put in order, but we can't necessarily calculate precise differences. Now that's not the one that doesn't have a natural zero. The next one, interval level, doesn't have the natural zero. Okay, we can put it in order, we can calculate precise differences, but zero doesn't serve as an initial kind of starting point. When we think about the number 0, usually we're thinking that's where things start. It starts from 0 and goes up, right? But if you could possibly go down past 0, or if possibly the value can never take on 0, then those things would be interval level data. Okay? Some standardized test scores would be at interval level data. They say just for showing up at the SAT you get 200 points. You know, nobody comes out with a 0. Okay? So that would be interval level data. Right. That's how we live in America. Okay, let's see. Mr. Bortz. Okay. Garvin, a statistics student, visits 4 local grocery stores and notes the prices of a 5-pound bag of potatoes and a 5-pound bag of onions. The results are listed below. From this data, he states that in his city, potatoes are more expensive than onions. His statement is an example of a population, inferential statistics, descriptive statistics, or probability. Okay, that's a good clue. She says we hadn't gotten to probability yet, so it's not that one. All right. Yes. Okay, all right, you were in the right ballpark, but it was C, inferential statistics. Okay, with inferential statistics, we go beyond our sample data and infer about the population. So it's a city. We debated about this yesterday, but I'm thinking a city has more than 4 grocery stores. Okay, so this would just be a sample, and so we're taking what we learned about this sample and making an inference about the entire population of grocery stores in this city. Okay, inferential statistics. Very good. You did a good job of narrowing it down. That was good. Okay. Charity Bowman. Okay, Social Security numbers are an example of what type of data? It's nominal. It's just a label, right? Your Social Security number has no numerical value. It only identifies you. Excellent. Okay, a baker reports that more people buy glazed donuts over any other kind. What measure of central tendency would be most appropriate for making this determination? Did Miss Carol come in? She's not here. Chelsea Collins? Okay. And now you wish that you weren't? I'm so sorry. Okay. What's the best measure of central tendency for the kinds of donuts people are buying? Okay. Think about the data. Go back to the basics of it, and say you're standing down at Krispy Kreme, and you got your little form, and you're writing down whatever it is you're observing. What kinds of things are you observing on each person that comes by? What they have is what? What are you observing? I'm sorry. Is it how many they're getting, or what? What kind they're getting, right? Our data is what kind. So we got glaze, we got the chocolate glaze, we got, the different ones. So now that we know what the data is, what's the best measure of center? B, the mode. Excellent. Very good. Okay. The mode. So that's always a good question. Go back and ask, okay, what is it that's written on this paper? What is it that we've actually observed? Okay. Ooh, who's next? Zachary. Okay. A sample of children's weights has a mean of 115 and a standard deviation of 22. At least 75% of the data will fall between what values? Okay. He says B. All right. I believe that B is correct. Which principle are we applying here? Okay. Chebyshev's theorem. Right? All right, this is about Chebyshev's theorem. And so we've got the mean, we've got the standard deviation, we've got a percentage, and they're asking us about some interval. Okay? So that kind of summarizes Chebyshev's theorem and the empirical rule. Okay? How can I make a determination between the two in this case? How can I decide whether or not I'm going to apply Chebyshev's theorem or the empirical rule here? Okay, by the percent, okay, the value. This is one of the values that was along with Chebyshev's theorem. Anything else that would indicate we're going to use Chebyshev's theorem? The mean, not the mean, because they give us the mean for both of them. It has something to do with you only use certain data with. Okay, very good. So it's normally distributed data goes with the empirical rule. They don't tell us anything about the distribution of the data. That's why we're choosing Chebyshev's theorem. The other little tiny clue, I think I emphasized this, was what? At least. The empirical rule says what? One bigger word. No, not always. That would be a good one. Approximately. Okay, the empirical rule says approximately. Okay, so got all that. I know I'm using Chebyshev's theorem. I've got 75%. If I think back, if I remembered some of those values, I think 75% corresponded to 2 standard deviations in Chebyshev's theorem. But if I wasn't certain, you could either say 1 minus 1 over k squared equals 0.75 and solve that for k. All right, and you would come up with k equals plus or minus 2. Or you could take a guess. If I put plus or minus 2 in here, does that work? And it does. It comes up to 75%. So to get this answer, what we do is x bar plus or minus 2s. Okay, or the mean is 115 plus or minus 2 times 22. Okay, so 115 minus 44, I believe is 93. Is it really? Okay. All right. And then 115 plus 22 is 159. So the answer is actually C. Okay. Questions about that? Yes. Well, not just that wasn't the only clue. Again, the fact that it didn't tell us anything about the distribution of the data. Okay, that goes along with this theorem. If it had said that it was normally distributed, then I would be using the empirical rule. Okay, but it didn't tell us anything about the distribution, so I had to use Chebyshev's theorem. Okay, does that make sense at all? A little bit. Okay. All right, I'm gonna let y'all ponder that. Okay, number 8. We gotta go fast. Ms. S.Q. Scott. What is the weighted mean of the cost of tennis shoes? How would we find that if you don't know the value? What would you do to find it? You don't know? Oh. Okay. She doesn't know. Okay. What about Ms. Guerrero? Can you help her? How do we find the weighted mean? No? Oh my goodness. Okay. Anissa Harlan? Oh, Lord, no. Okay, real quick. Well, you could do it by hand. Weighted mean is the summation of x times w divided by the sum of w. Okay, so we would take each value, each number, multiply it by the price, okay, and then add all that up. Then we're going to divide by our total weight. Now, here's something you need to ask yourself. Which one of these things is the weights? Would the weights be the number purchased or the price? Okay, it's actually the number purchased. Okay, what are we trying to find the average of? We're finding the mean costs. So that's our x. Cost is going to be our x value. Our weights would be the number purchased. If we were to write this data out, we would list 35 8 times. And then we would list 45 10 times. Okay, that's where the weight comes in. On our calculator, where's my calculator? Here it is. What I would do is put these numbers in my list. So stat, calc, oops, sorry, got to put them in the list first. Stat, edit. And, okay, I'm going to put, doesn't really matter which list they go in. So I'll put 8, 10, 14, 6. Okay, 8, 10, 14, 6. All right, we've got the numbers there. Here, I put, again, note, my x values are in L3 and my weights are in L2. So when I do my one variable stats, I tell it where my x values are first. So they were in L3, comma, which is right above the 7. And then I tell it where my weights are. They're in L2. And so we come up with $37.11. Okay, which is B. Weighted mean. Okay, make sure you go back over that. Not just this type of example, but the concept in general. Okay, Jimmy is constructing a pie graph to represent the number of hours his classmates watch television each day. He found that 11 out of 30 watched 2 hours a day. In his pie graph, this would represent how many degrees? Answer, let's see, Mr. Jenkins. What would we do for this one? Okay. And then what? We're going to multiply it by 360 degrees. That's right. Okay, so take 11 divided by 30. That gives us the relative frequency or percentage. Then we multiply that by 360. That comes up to be what? Okay, B, 132? Okay, very good. Excellent. Okay, hopefully by now you all know how to find these values. So for sake of time, we're going to skip number 10. Okay, Sandy and Dennis want to compare their scores on an English exam. Sandy got a grade of 80 on a test with a mean of 70 and a standard deviation of 8. Dennis got a 72 on a test with a mean of 65 and a standard deviation of 9. Which of the students had the better relative score, and what was that score? Okay, I'm just going to go with this. Which principle are we using here that we talked about today? Z-scores. Excellent. So I'll find the Z-score for Sandy. We're going to do X minus X bar divided by S. X is, for Sandy, was 80 minus 70 divided by 8. So I think that comes up to 1.25. Okay, and then for Dennis, we've got 72 minus 65 divided by 9. And that comes up to what? 0.77? 78? Okay. All right, 0.78. Get back on the screen. Okay. So, who scored better? Sandy. She's farther above the mean. Okay, she's 1.25 standard deviations above the mean in her class, versus Dennis is just 0.78 above the mean in his. Okay, so we would say the better student is Sandy. Sandy. With a score of 80. Questions about that? That's a good measure, yes. Okay. Data from two different sets. I would use a Z-score. Okay? Any questions? Anybody comparing this to what we did earlier and a little confused? Nope? Okay, good. All right, very good. Okay, all right, we got some quick ones here. So let's go back to our little list. Mr. Jimenez. Number 12 says, what is the width of the class 18 to 24? Okay, 6. All right, how many people agree with him? Okay. It's actually 7. Okay, remember the class width is the difference between what? Consecutive lower class limits or consecutive upper class limits. We don't do lower class from upper class. So my next class would start at what? 25. That's my next lower class limit. And when I subtract, I get 7. That's how we get 7. We didn't do anything with that. Now, if we added the 2 and divided by 2, that gave us the midpoint. Okay, maybe that's what you're thinking about. the boundaries would be halfway between. So for this class, it'd be 17.5 to 24.5. Okay, and then the next class, the lower boundary would be 24.5 to whatever 24.5 plus 7 is. Okay? Cameron Johnson. Okay. All right. A computer facility, at a computer facility, I don't know. Every 200th computer chip is inspected for defects. This is an example of what type of sampling? Systematic. Okay. All right, systematic. Very good. Okay? But make sure you go back and review all of the methods of sampling. Okay? Because I might not ask about systematic. I'll ask about something else. Okay? Luann Kirkland. Okay? Measures taken by using all the data values in the population are called statistics. True or false? That's false. Very good. Okay, it is false. If they're measures that describe the population, we call them what? Parameters. Excellent. Yes, very good. All righty. Okay. Okay. What about number 15? Ooh. Police chief wants to prepare a graph showing the frequency of each type of crime committed on a college campus. What type of chart should be used, Mr. Lewis? Andrew Lewis? What type of chart should we use? Pie chart, Pareto chart, time series, or histogram? To show the frequency of each type of crime? Okay, getting closer. What? One more time. The frequency of each type would be Pareto. It'd be Pareto chart. Okay. Now, if we talked about qualitative data, we'd certainly narrow it down to pie chart or Pareto chart. But on a pie chart, we usually display what? Percentages. They wanted to talk about the frequency. Okay. And so Pareto chart would be a better choice. You could put frequencies there on a pie chart, but when we talk about a pie chart, we need to make sure that the data makes up a whole. Okay? If it's possible for people to choose more than 2 categories, then a pie chart's really not the right thing to do. Okay? A pie chart shows how each category contributes to the whole. Okay, the biggest clue here is that he said frequency, not percentages. So I would use the Pareto chart. Well, first of all, it does, but a histogram is for quantitative data, and so we're talking about crimes. That's qualitative data. So you should ask, what kind of data do I have, and what is it that I want to display? Okay. All right. Okay. I guess I have to go somewhere alone and finish this video. We can talk about it a little more on